Welcome back to our statistical lecture series for our class. In this video, we're going to review Summers D, which is our first measure at assessing a linear relationship. Remember that lambda was for nominal relationships, and nominal variables do not have a rank order, so there can be no direction. With Summers D, we're assessing ordinal relationships, which are ranked variables. For these videos in this class, we're only going to focus on two types of linear relationships. Positive linear relationships, where as x increases, y also increases, and negative linear relationships, where as x increases, y decreases. There are, of course, lots of nonlinear relationships that we could examine in the world, such as curved linear relationships, logistic curved linear relationships, and the like, but we're not going to be focusing on those in this class. So here I have a two-dimensional graph where we have an x variable on the x-axis, rank low, medium, high, and we have a y variable on the y-axis, also ranked low, medium, high. Now for positive relationships, we can imagine a line running from the low, low part of the graph to the high, high part of the graph. And this is illustrated here with the blue line. We could also envision a negative relationship that runs from low, high, that is when x is low and y is high, down to high, low, that is where x is high and y is low. This is represented in the green line. So here I've overlaid both the positive line and the negative line, so we can start thinking about how ordinal relationships show up in what is essentially a crosstab. So positive relationships are defined by values in the low x, low y section of the crosstab, the medium x, medium y section of the crosstab, and the high x and high y section of the crosstab. Once again, this corresponds to the combinations of cells that we would see in the positive line relationship. Conversely, a negative relationship would be defined by values in the low x, high y cell, the medium x, medium y cell, and the high x, low y cell. Once again, this is reflected in that negative line and would be reflected in our crosstab. To illustrate a little more clearly, let's take a look at a crosstab that has an x variable. Let's call this support for labor unions that ranges from low, 1, medium, 2, and 3 high, against a y variable called support for Democrats, also ranked low, 1, medium, 2, 3 high. So to illustrate, I've run the positive line through the crosstab, which runs from low, low, through medium, medium, and into high, high. You'll notice that this is essentially the same relationship we saw in our two-dimensional graph. The only difference is that the line is flipped because the table is flipped upside down. That is, where we have the x-axis on the bottom in our two-dimensional graph, the x-axis actually appears on the top in our crosstab. Once again, we can completely flip that line, and that'll reflect our negative relationship. So here in our two-dimensional graph, we've got x low, y high, x medium, y medium, and then x high, y low. The blue line in our crosstab now runs through x high, y low, x medium, y medium, and then finally x low, y high. Once again, you can just kind of flip it upside down, and you'd have the same relationship in both visualizations. So the question now is, how do we actually use data in the crosstab to assess a relationship based on this conceptual structure? So the calculation of Summers D is equal to C minus D divided by C plus D plus T. This is really quite confusing at first glance, but after you think about what each of those different letters mean, it really kind of falls into place. So C refers to what we call concordant pairs, which are any pairs of observations that support a positive relationship. In other words, concordant pairs are positive pairs, or positive relationship pairs. A discordant pair is the opposite of a concordant pair. It's a pair of observations that supports a negative relationship, so I call these negative pairs. Finally, we have tied pairs, which are pairs of observations that are neither positive nor negative. So looking at the calculation, we're going to take the number of discordant pairs and subtract it for the number of concordant pairs. In other words, if the number of negative pairs outweighs the number of positive pairs, Summers D will be negative. If the number of positive pairs, that is C is greater than D, outweigh the number of discordant pairs, then the relationship will be positive. The difference between concordant and discordant pairs is taken as a fraction or proportion of the total amount of pairs in the data. That is, concordant pairs plus discordant pairs plus tied pairs. So how exactly do we calculate a pair? Well, a pair is simply any two observations that we can connect to draw a line. So for example here, if we're thinking about positive relationships run through low x, low y, medium x, medium y, high x, and high y. That means that we can draw several different pairs or connect several different pairs to support a positive relationship. Low x, low y connected to medium x, medium y forms a positive pair. Low x, low y to high x, high y also forms a positive pair. Finally, medium x to medium y to high x, high y also forms a positive pair. Let's take a look at an example. So suppose here that we calculated our crosstab and we only had observations in the cell entries we see in the table. We had 10 low x, low y, we had 10 medium x, medium y, and we had 5 high x, high y observations. What we'd be looking here to do then is form as many pairs as possible given our existing data. So to do that, we would first look at our concordant pairs, our C's. In this case, we'd be looking to connect each observation in low, low to each observation in medium, medium, each observation from low, low to each observation in high, high, and from each observation in medium, medium to high, high. The way to calculate this then is to calculate the pairs for each combination of cells by multiplying the values in those cell entries together. So if we have 10 entries in low, low and 10 entries in medium, medium, we can make 100 pairs. That is, each individual observation in low, low can be paired with each observation in medium, medium. So for each one observation in low, low, we get 10 pairs with each observation in medium, medium. When we do that over 10 observations in both sets, we get 100 pairs total. Similarly, we can take our 10 observations from low, low and pair each of those with our 5 observations in high, high. 10 times 5 gives us 50. Finally, we can take our 10 observations in medium, medium and pair each one of those with our 5 observations in high, high for another 50 pairs. That gives us a total of 200 concordant pairs. That is, from the data in our table, we can calculate 200 pairs that support a positive relationship. Conversely, if we flipped our data around, we could calculate discordant pairs going through the other diagonal. Here we have 10 observations in high, low times 10 observations in medium, medium for 100 observations, or pairs. We have 10 observations in high, low times 5 observations in low, high, and that gives us 50 pairs. Finally, we have 10 observations in medium, medium times 5 observations in low, high for another 50 pairs. Now keep in mind, if we had data in the second table, this table, we would have 0 C's, so 0 minus 200 D's would give us negative 200. Because there are no C's or T's, we'd have negative 200 over negative 200, which would give us negative 1.0 for a perfect negative relationship. Now that we've taken a look at a perfect positive relationship and a perfect negative relationship, let's calculate Summers D for the crosstab I presented. Here we have observations in all of the cell entries. So our first step is to calculate concordant pairs. Once again, this is calculating all the pairs that run along that positive line. Low x, low y, medium x, medium y, high x, and high y. We've already done this in our previous example, and we know that the concordant pairs in this case is 10 times 10 plus 10 times 5 plus 10 times 5, which gives us 200 concordant pairs. Discordant pairs run along the other line, so low x, high y through medium x, medium y through high x, low y. So here we have 2, which is our high, low, x high, y low, 2 times our medium, medium, that gives us 20 pairs, 2 from our high, low times 5 in our low, high for 10 pairs, and finally 10 from our medium, medium times low, high, 5 gives us 50 pairs. This gives us a total of 20 plus 10 plus 50 for a total of 80 discordant pairs. Finally, we need to calculate our tied pairs. I should note here that tied pairs are calculated by multiplying cell entries across the rows, not cell entries down the columns. So here, to calculate my tied pairs, I'm going to multiply low x, low y against medium x, low y, low, low against high, low, and then medium low against high-low. So for instance, looking at our first row, I'm multiplying 10 times 3 for 30, 10 times 2 for 20, and then 3 times 2 for 6. We do this for each one of our rows. So for our middle row, we're looking at low medium times medium medium, low medium times high medium, as well as medium medium times high medium. So we have 0 times 10 for 0, 0 times 4 for 0, and 10 times 4 for 40. Finally, moving on to our last row, we've got 5 times 1 for 5, 5 times 5 for 25, and 1 times 5 for 5. I put all these values in our Summers D formula just above the table. Right now it's simply then arithmetic to solve for Summers D. Simplifying the equation down, we get 120 over 411, which gives us 0.29. So how do we make sense of this value? Well, Summers D is always going to be bound between negative 1.0 and positive 1.0. Negative 1.0 representing, once again, that perfect negative relationship where all of the data are aligned along the negative line, or we only have disconcordant pairs. Positive 1.0 reflects a perfect positive relationship when all of our data are aligned along the positive line so that we only have concordant pairs. Obviously, when we add in disconcordant pairs, concordant pairs, and tied pairs, we're going to get something between negative 1 and positive 1.0. The sign of Summers D always tells us the direction. So if we have a negative sign, we have a negative relationship. If we have a positive sign, we have a positive relationship. The actual value of D tells us the strength of that relationship. The important thing to keep in mind about the strength of relationship is that it's symmetrical around 0. That is to say, if 0 represents no relationship and plus negative 1 represents a perfect relationship, then any value on the negative side is mirrored in strength on the positive side. A lot of students get confused and think that, for instance, a positive 0.4 is a stronger relationship than a negative 0.6. Once again, keep in mind that the relationships are symmetrical, so in order to have a relationship that's equally strong on the positive side, it would have to be the same value it is on the negative side. So in this case, a negative 0.6 is a stronger relationship than a positive 0.4. For most of the part, you're going to have to interpret Summers D because SPSS does the calculation for you. However, the way it works is we are always looking for how many observations support a positive relationship against how many observations support a negative relationship over all the relationships we have in our data.